Good morning, guys. All right, here we go with lesson number 3 for topic 5. So we're moving a little bit in a different direction. The other two things that we did were review. You guys already knew how to use Q equals MC delta T, and that should have been reviewed. Some of the questions were a little bit more difficult than last year, but in general, you are basically either solving for Q or M or C or delta T. But there are different ways of calculating heat that is being released or absorbed during a reaction. And that is what we're going to talk about next in topic 5. The next few things that we're going to be talking about are going to be brand new. Okay. So let's start by talking about how IB wants you to know that there is a difference between heat and temperature. They are not the same thing. Heat is a form of energy, while temperature is defined as a measure of average kinetic energy of particles. So heat is a form of energy. Temperature is the measure of the average kinetic energy of particles. So, when particles are moving, the more they're moving, the higher temperature. The lower temperature, they're not moving as much. Like when something is frozen solid, the particles aren't moving, so they don't have a lot of average kinetic energy. Okay, next slide. And again, you should have all this written in your notes already. And if you don't, you're behind. Okay, if there's a transfer of heat between the system and the surroundings, then the reactions are exo or endothermic. Again, you guys know this already from last year. This is a review. Exo meaning exit, endo meaning in. Exothermic, heat goes out. Endothermic, heat goes in. Now, something to remember that in chemical reactions, total energy is conserved. So energy isn't created or destroyed. It's just changed from one form to another. Okay, so just remember that energy can change from one form to another. There's different types of energy. There's electricity, there's heat, there's all different types of energy that you guys should can look into, and it's just changing from one type of energy to another. Kinetic energy, like we talked about, potential energy is something else you learn about, like in physics. Okay. All right, here we have, at the very bottom here, we have energy of bonds breaking should be equal to the energy of the bond formation. What that means is that when a chemical reaction is taking place, the reactants are originally breaking their bonds. They break their bonds first. And because then they'll be able to move around and get rearranged and form new products. When they form new products, then what happens? Then the bonds form. So that's the energy of the bond formation here. So bonds breaking is the reactants, bonds forming is the products. And then, of course, altogether, you must also take into consideration the energy that's being input or output. In other words, endothermic or exothermic. Okay, guys, we have to learn 4 different ways of calculating delta H. Do you remember delta H from last year? We learned about enthalpy. It's another word for heat, but it's like enthalpy given. It's the heat that is required or given off during a chemical reaction. So the units of enthalpy are kilojoules per mole. The delta H values are going to be given in standard form in the following notation. Delta H with a little theta symbol at the top. That means standard state. And standard state is not the same as standard temperature and pressure. So that's something that I want you guys to make sure that you note, that standard state is SATP, and that's 100 kPa and 298 Kelvin. Whereas STP is standard temperature and pressure, and that's 100 kPa, but that's 273 Kelvin. So they're a little different. I will tell you that both of those values are given in the data booklet, so you don't really have to memorize those. Next. Okay, here's the first delta H I'm going to teach you how to calculate. So the standard enthalpy of combustion. Okay, so let me tell you something really quick. There's going to be 4 delta H's that there's going to be 4 different types of ways of calculating delta H. Only 2 are like really important, and they test you and they want you to really practice. This is not one of them. but you're still going to learn all of them. Okay. I'm still going to teach you all of them. So right now I'm going to do the first two. The standard enthalpy of combustion of a compound, it is going to look like this, delta H with a little c on the bottom. The theta, remember, means that it's at standard state. The enthalpy change, which occurs when 1 mole of the compound is burned completely in oxygen under standard conditions and with everything in its standard state. Okay, enthalpy of combustion. So I asked you to look at your data booklet because you need to go and in your data booklet, it will give you in the, what's it called? Table of contents. They'll tell you to go to page 13. And on page 13, you're going to find this. Look at that. Enthalpies of combustion. So you're given some values, okay? So we are going to do an example. So here is the example that I have in the notes. Okay, this is how you're going to calculate it. You're going to take the sum of the delta H of the products and you're going to subtract the sum of the delta H of the reactants. Again, this is the formula. Take the sum of the delta H of combustion of the products and subtract the sum of the delta H of the of combustion of the reactants. So you're gonna have to use your data booklet. Now, I've already looked this up. I think you guys should, after you watch this video and while you're watching this video, you should look up the values. I'm gonna go over how we do this example right here, okay? So I'm gonna go to my paper. So guys, I've got here the equation. Carbon plus hydrogen gas makes methane. You guys should know that. Here's the formula, the sum of the delta H of the products minus the sum of the delta H of the reactants. From page 13, I got these values. Can you please confirm that for methane, it should be negative 891. For hydrogen, H2, it should be negative 286. And for carbon, it should be negative 394. If I take these values and I plug them into the formula, again, remember, look, products minus reactants. The product, there's only one, negative 891, minus the reactants. What do I have? I have the negative 394 from the carbon plus 2 times the negative 286 of the hydrogen gas because of that coefficient 2. Okay, so then I do the math. I get negative 891 plus 986 gives me 75 kilojoules per mole. And since it's a positive value, we would say that this is an endothermic reaction. Positive value means that it's an endothermic reaction. That's how you do, that's how you find the enthalpy of a reaction using enthalpies of combustion. One more time, that's how you find the enthalpy of a reaction using enthalpies of combustion.